talk is conductive polymeric filaments for additive manufacturing. Can we rely on their performance? My name is Ana Paula. My co-worker is Ana Catarina, which is also online. I was not sure to arrive in time. And I'm from the University of Coimbra in Portugal. And as you see in the top, my university is one of the oldest in Europe. She is from 1219, okay? And for those of you that only heard about Portugal because London, Algarve, or Cristiano Ronaldo, I can tell you that Coimbra, it's a small town halfway between the two major cities of Portugal, which are Lisbon and Porto. And this is how Coimbra looks at night, and you can see on the top of it the university. The old university that is from the 2013 World Heritage by UNESCO, okay? And just to give you a glance, this is the throne room where we pass our PhDs, okay? So in a stressful moment of defending our PhD, they induce us more stress by putting us in this room, okay? But just a small presentation. Let's talk. Why did I make the question, can we rely on the performance? Well, just to tell you that we had made a purchase of commercial filaments of TPU and PLA, nanocomposites, that had or were supposed to have antimicrobial properties. In fact, we have here the tests for Escherichia coli, and we have TPU. Let me just put the laser. Okay, and we have here simple pristine TPU and PLA, and as you see, the bacteria grow because they are not antimicrobial. The composites with copper of these polymers, if you take them away from the place where you put them, you see that no bacteria have grown. So the filament has in fact antimicrobial or antibacterial properties. The fact is, when you process, and we have processed it with the several infill and geometries, densities, whatever, and we have tried with Escherichia coli, Staphylococcus aureus, and Pseudomonas aeruginosa because they are in the top 10 of the most dangerous bacteria and infectious bacteria, and none of them present any antimicrobial property. So the problem is that what is advertised for commercial filaments may not be true once you have printed your specimens, okay? So, in fact, motivation does the same happens as with antimicrobial properties, with other properties. Does the processing by additive manufacturing, in this case FFF, always annul the commercial filament properties? So let's try it with electrode properties. So we bought Filaflex, which is a TPU-based polymeric matrix, which has advertised as a conductive reinforcement of lump black, and in color it was black, and Coltron G1, which is a PVDF-based polymeric matrix, and in principle is advertised with a reinforcement of conductive graphene, okay, also black. So as usual, we made because we don't rely very much on what they say, sorry, but we make some basic characterizations of the filaments. The first of all was the FTIR, just to see if we have the main chemical groups that are supposed to be in the material, and on the other hand, because we don't know if it is a polymer or a plastic, they are plastics, because at least they have the pigment additive, because no polymer is black, or blue or red or yellow or whatever. So let's see if the percentage of additives does not superimposes to the chemical groups of the polymers themselves, okay? So then we made to see the thermal stability in order to have an idea of the temperatures where we should process the polymers during printing process. And what we saw is that in fact we have stable polymers around 310, 340 degrees Celsius. Of course, PVDF based filaments, it's more stable at temperatures. Nevertheless, we are not going to go to printing at this temperature. Also, we saw that we have 30% of char for Filaflex and 46% for Coltrane. When we compare this percentage of char with those of the TPU and the PVDF non-composite materials, so the thermoplastic materials, we know that we have more or less 15% of reinforcement in weight for Filaflex and 30% for Coltrane. Okay? Well, another characterization was DSC, and we saw that they were semi-crystalline, and the TG of both and the TM were determined once again to go to the temperatures that we should process the polymers. We made the morphology of the filaments after after tensile test, and what we saw, in fact, is that at least in the region of the fracture, very low density of reinforcement. Okay, we see that the lump-like, that they will call it, is these filaments, these fibers that are in the area of the fracture with very low density. You see small amounts. Of course, you can see perhaps a low density of reinforcement here. That's why the reason it to fracture in this region. Okay, so, and when you go to Coltrane, as they say, they are rings of graphene. We don't have, our microscope didn't have the resolution to see if we have any flakes of graphene among there. So you have just an almost more or less homogeneous aspect of the filaments. Okay, so we process it. We made traction filaments according to the ISO standard, and we print them at 230 to 60, bed temperature 40 and 60, and printing speed very slow because we wanted to, it was not easy to print, mostly the PVDF based polymer. Okay. Now for the electric measurements, we try several things. First of all, we try with a simple multimeter, and we made a painting with silver just to enable the contact more easily, okay? And we measure the resistance, we calculate the resistivity and the conductivity, okay? And what we saw is with this technique, we have always less conductivity in the printed specimen that we had in the filaments, okay? Please, I didn't tell you, but the printed specimen have an 100% in field of plus 45 minus 45, which means that the filaments and the reinforcement may not be aligned in the direction of the testing procedure, and that's why the reason, maybe the reason of this less conductivity for the printed specimens. And then we made a more sophisticated, let's say, test where we made both for filament and for printed specimens. We wanted to measure the resistance or resistivity or conductivity, in this case resistance, values during the tensile tests. But as this was a new approach, we also measured before starting with any force or having any displacement. And once again, what we saw is the decrease of conductivity, the increase of the electric resistance once you have the printed filament. And the values that we have with this method regarding the other with the multimeter were were lower than the ones obtained before. And this in principle should be because we don't have such a good contact between the parts that are measuring and the polymer, printed or filament, as we had when we painted with silver the ends of the filaments, okay? During the test, what we saw is that with Filaflex, the filament, as you apply force, you almost maintain the electric resistance up to a value, then the electric resistance begins to increase, okay? In the printed specimen, what you have is that you have initially an increase of the electric resistance, but afterwards you have a decrease. The more or less same results were obtained for Colton, more or less, I say more or less, because the non-constant value measurement was absolutely catastrophic in Colton. And we think this is related with the morphology of the reinforcements. And then we made, in the elastic deformation region, cyclic measurements, okay? So with a maximum force of 5 newtons, 100 cycle, only in the printed specimens. As expected, due to the viscoelastic properties of the polymers, we have a constant deformation. Filaflex TPU based, what you see, in fact, is that during the cycles, you begin to have a very big percentage of constant deformation of the printed specimen. But what it is interesting is that the electric resistance begins to decrease during the cycle, which means that if we use these polymers, these printed in components that are subjected to mechanical solicitation, you don't have problems with the values of conductivity, because in fact they will increase during the test. And what you see is that you have a pattern in the values of the electric resistance when you apply force or when you remove the force from during the cycle test, okay? In Colton, of course, PVDF won't have the deformation that was presented before. I maintained the scale so you can see that this behavior is very different of this one. And also the main tendency is that you have a decrease in the electric resistance, so an increase in electric conductivity when you are making the cycle tests in your material. So the main conclusion is that what they call the lump-like whatever reinforcement is in fact fibers, okay? The TPU has higher electric conductivity, both as filament and as printed specimen, was something that is more or less expected, either because of the softness of the matrix, but also because of the morphology of the reinforcement. And the electric conductivity of the printed species increases during the tensile strength tests, which it is really, really interesting, okay? So, in fact, the electric conductivity is slightly decreased by the processing technique during the processing of the composites, but it does not happen as the antimicrobial properties, where you have zero of the antimicrobial properties. Okay, I would like to thank my students and my colleagues, Andrea, Mahmoud, and Anna Caterina, and of course the projects that have sustained this research. And of course, thank you all for listening, and if you have any questions, I'm available.